is Jane Yan. Dylan is going to be giving us a wonderful talk relating to emulation and real-time analysis, and we're getting some actual real-time lighting going on here right now. So without further ado, I will turn it over to Dylan to give his talk.
Thank you for the introduction. Very good. Hi everyone, my name is Dylan. We're going to be talking about some pretty cool stuff today. I made a tool last year that this talk is going to be about for doing better gadget searching, or I'm a little biased, but I think better using like really constrained search queries and emulation to do analysis, like contextual gadget searching as well with different features for defining that context. So on screens, my email in case you want to contact me. I have a blog post related to the research. And a huge shout out to DistrictCon Year Zero. I'm a first-time conference speaker, and I'm super honored to get to talk at such a cool conference. It's nice to have something like this in the DMV, so huge thank you to them. So a quick thing about the agenda before we actually start talking about anything. We're first going to be talking about what ROPView actually is, what separates it from sort of other tools. We'll be going over the components, all the different stuff that enables ROPView to have the cool features it has. I'm going to be giving a quick primer on the Unicorn engine, just in case anyone's unfamiliar with CPU emulation or Unicorn. We'll be going over my gadget analysis framework and how that works to make really compact but accurate emulations. We'll be going over the data analysis aspect of it. That allows for all the constraint stuff you can do with ROPView. And the semantic search feature. We'll be going over some demos, some real life applications that I've actually used ROPView on. And we'll be going over some pitfalls and potential remediations. Won't end on the bad note. So before we get too deep into any of the actual content, quick who am I? My name's Dylan. I'm a junior computer science student at George Mason University. I have experience with REVR and embedded, but I'm interested in other areas. I'm trying to get into mobile right now. I got lots of extracurricular. Some of the more notable ones is I'm the current president of George Mason Cybersecurity Club, and I'm the founding engineer at a AI recruitment startup called Barty. I'm interested in emulation, automating weaponization, and tooling. I think an engineer should be able to focus more on techniques and overcoming different constraints than simple or semi-simple stuff like, coming up with a ROP payload. So that's the main goal of this tool. All right, let's talk about ROPView. Raise your hand if you use Ghidra or IDA. Okay, I can fix you. So ROPView initially, it's a binary ninja plugin. Initially, it was just sort of an inspiration, like a spiritual successor to iDesploit, but it's become so much more than that and more featureful. It is a gadget searcher, but it's also an analyzer. So you can do stuff such as you can see on the screen here, on your right pane, you have gadgets. On your left pane, you have analysis. So you can just scroll down your gadget list and look at the after analysis and immediately see the memory state the gadget leaves the binary in, the loaded binary. So we'll show you hey, I have full control of this register, or this gadget writes this value at this address. And so I made a deterministic and self-resolving emulation algorithm that basically lets bad stuff happen and just continuously fixes the current emulation context in accordance with the binary or the core file. And it's super lightweight, even with analysis steps and the hooks that it uses. Emulation is fastest when there's no hooks. And still, when you scroll down the gadget pane, you'll get instant analysis results. Semantic searches aren't instant, but they're pretty quick. Before I go too deep into the gadget analyzer, actually, I'm going to do a quick primer on Unicorn Engine in case some people here aren't familiar. It's a lightweight contextualist CPU emulator. What that basically means is you can just map some memory, write some machine code, and emulate it without actually having to worry about anything, which I think is pretty cool. So there's no special setup. You don't need to like make a valid structure or anything. So it's pretty useful when you're reverse engineering. Like, let's say you encounter like a bootloader that's decrypting something into Flash or maybe a second stage. You could just rip that off the ROM, put it in Unicorn, emulate it, and see what it does. It has easy to use Python bindings, and it has lots of implemented, it also has lots of non-implemented hooks, but the ones ROP use are obviously implemented. What we're using is the code block hook for per instruction analysis. That hook is executed when an instruction is fetched and before the instruction is executed. And the second one is kind of simplifies. We're actually using a lot of hooks here, a lot of different CPU violation hooks. We're handling both recoverable and non-recoverable errors. So like a non-recoverable error would be like if a gadget causes like a null dereference or tries to execute read-write code or something. That's like a problem with the gadget. I don't care about that. But if it's recoverable, like the gadget's trying to fetch some memory that's not mapped into the emulator but exists in the binary, that's where we're going to do some cool stuff. Some drawbacks with both, mostly emulation, not really just Unicorn, is that hook's slow emulation. Again, an emulation runs fastest when you just start it and let it run. When you're executing a hook, you're sort of pausing it, leaving the emulator to execute that hook and then resuming it. And also emulations are space complex, especially if you're like spawning a bunch of emulations on worker threads, and if you're using emulations in a modulated tool like this where there's also like gadget analysis objects. We need a way to make sure the garbage collector can find all that and get rid of it. On the left here, or on your guys' right, is just an example of some Unicorn code, pretty simple. We're mapping a text segment, we're mapping a stack, setting the stack pointer, just running it, very easy to use. Onto the cool part, the analyzer. To go more in depth with the left pane you all saw earlier, in the red we have a before analysis, in the orange we have a per instruction analysis diff, and in the green we have an after analysis. So if you're just trying to sort of find a good gadget based on memory effects without actually looking at it, you could just dart your eyes to the green in the analysis pane and find that, just scrolling down or search for it. So this is a pretty simple gadget to use as an example because it's one instruction, but I think it's still a pretty good gadget because it shows like how verbose it can be, saying that we wrote DCBA into an address that's an init array, and we're assuming it did that because of some pre-state. The analyzer emulates and caches effects of selected items, and it also handles search queries by populating a bunch of analyses. The issue with making an emulation algorithm like this is gadget emulation should be small, but they should have precision. We want small emulations because we don't want to keep spawning huge ones with the entire binary context, but we also we want them to be accurate. We want a gadget like this to actually work in context with the binary that's loaded. So we need a way to handle that. And the algorithm I'm about to show you is pretty simple, utilizing Unicorn hooks to recursively call into itself. I find it pretty fast as well, and I think it's pretty cool because the end result is every gadget has a different emulation of a different size, different memory mappings, but they're all the absolute smallest they can be while still being accurate. The resolver and analysis steps, so these are the two hooks we're using. The analysis hook is for analysis, not for actually fixing emulation. So that just executes, again, in between fetch and execute. And it does a memory diff on registers and memory locations. We have CPU exception hooks. I explained recoverable and non-recoverable, and we're going to see more of that in the next slide. So here we're going to go over an example of a gadget being used in the gadget emulation framework. So I'm going to use the gadget from the previous slide. The only thing I changed are the memory locations. Assume R14 is a valid address in the binary. Here at initialization, we're going to do stuff like just set up the Unicorn object. The only thing really special we're going to do is we're going to fill the stack with syslect data. That way, when we're doing analysis, if a register contains syslect data, we can tell we actually got full control of that register from the stack, and we know the offset where we got control. So we wrote that gadget to the text segment, we set up our stack, we're ready to start. We enter the emulation function. We're going to hit the violation resolver each time. Right now the resolver queue's empty. Remember, we let bad stuff happen. Nothing bad has happened yet because nothing has happened. So we're going to move right to the emulation start. That's going to be fine. The analysis hook is also going to be fine. We haven't actually executed the gadget that causes the access violation, and there's also nothing to diff, so it's going to be a pretty quick function call. But once we execute that gadget, we're going to get an unmapped write error. This is because, again, we're trying to write to this address. It does not exist in the emulation. So we're going to recursively call back into the function. The resolver key is now going to have something in it. So we can't really start emulation until this is resolved. We're going to head to the real-time resolver. The real-time resolver is going to calculate the nearest page-aligned boundary for that address and the minimum size needed to overlap the violating address. And it's going to reach out to Binary Ninja and ask for the data and write it into the emulation. So now we actually have the real data from the binary in our emulation context. Resolver queues dequeued. We start emulation. Analysis hook, again, this time's pretty fast. Now we succeed the violation hook, and we cache that gadget so we don't have to emulate it again until something violates integrity of the cache. Let's go to the actual data analysis part. We use pandas here. So every searchable thing you can enter in the search query is a pandas object. So that means you can use all the pandas functions you want to do your searches. Again, the search filter is a really simple interpreter, basically. So I'm not going to go over all of these attributes. A lot of them are pretty simple. I'll mention a couple special ones. But for example, you could do disassem.contains pop-rax because disassemb's a pandas string and contains a function you can use on that. I don't have the full list of functions, obviously, but there are a lot. So it makes for very good queries. I'm also sort of piggybacking off of pandas. Pandas has really good, you could make large logically combined constraints, and we also have our special searches here, like the semantic search on screen. So we can combine a bunch of stuff and then translate it on the back end of ROP view and make that search pretty easily. I think I should actually talk about the special search going on screen right now. So this is a semantic search. So we're searching for a register value. So we want to get back all gadgets capable of making R0 equal OXDeadBeef, which is pretty much just going to be gadgets that give us stack control. When we actually run that, the pandas query that gets translated into is register or R0 equals OXDeadBeef or R0 equals full control and not R0 equals not analyzed. Full control and not analyzed are sentinel values. When we initially start ROP view and we're not restoring from some sort of project, all the registers are going to be preset with the not analyzed value until we actually make a search or scroll down and do some analyses. So in order to make gadgets not have that sentinel value, we're going to have to actually populate analyses, which is what the semantic search is going to do and what I'm going to talk about more in the next page. So this is semantic search. This is a much easier algorithm than the previous one. Really simple. So when we make a semantic search, we're first going to create a subdata frame and take it off the main data frame. This data frame is going to just contain critical registers that we search for. So only gadgets that actually touch that register are what we're going to actually emulate. We're going to go down to the population analysis. And this is based on a depth parameter. This is also one of the algorithmic issues I'll talk about in pitfalls. But right now we're just using a depth parameter that's going to determine how far we go with the emulations. And I found a good number that works most of the time. Obviously you can increase the depth. It's available to change in options. And you will get more results from your semantic search. Just be aware of the overhead that may cause. When we actually populate our analyses, all these analyses run on the main thread and wait, which sounds slow, but as I showed you earlier, or in the example semantic search, it's still pretty fast, less than 10 seconds. And of course, everything's cached, so you won't have to wait as long next time, because it's probably going to return some of the same gadgets if you make the same semantic search twice. After we actually make sure there's a pool of gadgets that have a full control sentinel or have the values of their gadget, when you run a gadget through the emulator, all the registers are no longer going to be not initialized because something's going to happen to all of them. Because we have pre-states. We're going to make a pandas query on that data frame. That's the same as I showed you before. So we're going to translate that, and we're going to replace it in the query, and then we're going to run the full pandas query, just in case you added more constraints, additional semantic searches, whatever, right? So some demos. This is the first one. There's no semantic search, so it returns the search instantly, but you can see how highly constrained it is. This is sort of a real-life example with added constraints just to like flex the tool a bit. But the actual query that matters the most is going to be the middle query. So this is a situation where we found a buffer overflow, but in order to reach it, you had to survive XML parsing, so the payload had to be ASCII constrained. So this constraint here is just saying, like, I don't care what the two most significant bytes are, but the rest of it should be ASCII constrained for like a partial overwrite or something. And we're also saying we don't want the location to have a null byte, and we want the location to be greater than 0x10,000, just for no reason. So, yeah. This is our first example of a semantic search. This is also our first example of an architectural preset. This is a MIPS preset. We can see how fast the search completes, and this binary has 82,000 gadgets, so it's pretty fast. It's also MIPS, which don't quote me on this, but I imagine would be harder to emulate because of delay branches and all the dereferences happening. So this sleep underscore A0, I mentioned it earlier, translates into two logically combined semantic searches. A0 needs to be greater than 0, and A0 needs to be less than 600. A common gadget, you might want to do a context switch and maintain cache coherency on MIPS. So we see that complete pretty fast. We're scrolling down the results and we see the analyses on the right. That's a pretty bad gadget, offset at 14,000, but there are lots of good ones, so let that run one more time. Yeah, so we can see all these gadgets give us a value in A0 that's small, or gives us stack control of A0 so we can make it small. This is another example, no semantic search again, so it returns pretty fast. There's one architectural preset, it's an x86 preset, it's pop return, PPR, and then just a bunch of random stuff. We see we're, again, using pandas functions directly on these objects, and address is less than whatever. So you can combine any number of semantic searches or constraints you want. It's the beauty of having like a search filter that's like a light interpreter. And another example of an architectural preset is also a bunch of logically constrained semantic searches. So this preset says I need a value of RAX that's 59, I need to have control of RDI, I need RDX to be 0, et cetera, and a syscall. So this is just for finding gadgets that can help you do an exec VD chain. So we run that, we see it's pretty fast. This is on libc, 19,000 gadgets, and we get those results. I'll let it run one more time because this GIF is kind of fast. I'm sorry if I pissed anyone off by saying GIF. There we go. All right, some pitfalls. It's not all great, as much as I'd like to just stand here and tell you all that. It's perfect. The first one is an algorithmic issue with semantic search. We need to know when to give up. If you are asking your headline using a depth parameter and not a success parameter, it's because what if there are no successes? For that MIPS binary, if we didn't find something that matched the semantic query, we'd emulate all 82,000 gadgets. That's going to take a while. It'll probably crash binary Ninja. So we need to find a way to tune semantic depth accordingly. And if anyone's interested in that, feel free to make a pull request, right? Stack accuracy. So as I mentioned in the initialization step of the resolving algorithm, we're actually writing Sicilic data to the stack. So our emulator stack lacks the real stack context. This is not actually accurate all the time. If you're using a core file and you're doing something weird like dereferencing a value on the stack without using the stack pointer, you will get the real stack data. But normal, sane people use the stack is not going to be accurate. It's the only mapping in the binary or dynamic regions that won't be accurate to the actual context. So we need to figure out how to deal with that. And then we're limited by dependencies. I'm mainly pointing out Unicorn Engine. It's a great tool, not great documentation, lacking lots of different hooks that you might find useful. And it's pretty limited in its ability. If you were to expand the scope of this project, you might need something capable of doing like interrupts or syscalls. But it's good. It does have its downfalls. I remember like 2 years ago, I filed an issue on Unicorn. When I was using the same code hook I'm using right now for analysis, and doing that on a MIPS binary, it would just not execute the delay branch. So it kind of like made me mad, and I stopped using it for that. But besides that, most of the time it's great, and it works here because we're not actually caring about what continues after the gadget. So ROP view's out now. Version 2 was released today just for this talk. You can find it on the repo, and you can clone it into your Binary Ninja plugins folder, or you can install it off the plugin manager. I pushed the release tag out this morning. Feel free to use it. Pretty nice to have if you're doing CTS or whatever, or embedded research. And thank you all for talking. I'll open the floor to questions. If any of you also have questions that you like just don't want to ask in front of anyone for whatever reason, you can find me in the conference halls. But thank you guys so much for coming.
Do you have any support for ASLR, or is it mostly just the state where the crash happens?
Yeah, it's going to be the state where the crash happens. Assuming like pi is also on, it'll be just the offset in the binary. So.
Is there any analysis on like the variant binary ninja IL instead of actual assembly?
So we're not, right now I'm not using any ILs. I'm disassembling it with Keystone and just sort of emulating it off that, just based on the fact that the gadget searcher is looking at the raw data and not using IL, because like some instruction sets could be like offset, so.
Yeah, my assumption is like that'd be difficult to emulate it so that you can't unicorn IL, but you could write your own IL emulator. But it would be kind of interesting from automatically getting free ROP support for any binary ninja architecture.
That would be cool. Also a unicorn plugin would be cool, so. All right. Thank you guys so much for coming. I've enjoyed talking with you. Enjoy your conference.